All right, I think I'm going to start in just a moment. For those of you just coming in, if you haven't looked at the wiki in the last 2 hours, this website is posted there, and you may want to go on and go there because you'll want to see what's there. So I probably have enough material for half an hour or so, and then we can do questions or discussions, however you want to do it. So I want to start from the wiki and show you a couple of things. So here, going from the background reading to the lectures, at the top item, Anjor Kanakor, who's one of the students here, found that Karsten Freegard has just posted, like a few days ago, 6 days ago, something like that, a version of Gadget 2 that's fully functional, that's already optimized for your laptop CUDA. So you can already run your problems on your homework on your laptop if you like, and it'll run about 30 times faster than on your CPU. So the first link is fairly useless. The second one, where it says go get it, is the link you want, and that's the one that I showed you a moment ago. So if we go there, this is what you get when you go to the link. I don't know who this gentleman is. He's in Denmark, is all I've ascertained. He has lots of Astro, so some of you might know him. But if you go all the way to the bottom, he's worked on Gadget for a few years. You can see that he's written some Gadget add-on code. And when you get to the bottom, you find G2x Gadget Optimization using the CUDA architecture. So this is a good thing. It uses the GPU multiprocessors found on your NVIDIA graphics card. Optimized code is developed on what I think is the latest CUDA support, the latest release. So if any of you downloaded to get ready for this meeting, you'll have the correct CUDA. If you downloaded a few months ago, you'll want to upgrade your download, from NVIDIA so that you'll have a compatible set of sources. You get new features too with 2.2, so that's a good thing anyway. And the beautiful thing here is you'll have source. First of all, you'll have 5 lectures on what is smooth particle hydrodynamics. So you'll know the physics and you'll know the decisions that were made at every point in the algorithm, or at most of the points in the algorithm. Second, you have the original C code so that you can see how the things were programmed. And then, as we're going to go through here for a moment, you'll have the CUDA code, which expresses the parallelism of the graphics processor, manages the memory, does the things that I've been talking about in a setting that you're familiar with, and should run on your laptop. So give you something to do this weekend if you're not going to New York City. What he says here is that speed-ups of the dominant part of the code, force, tree, evaluate, short range, is about a factor of 30. And the overall performance improvement is a factor of 10 to 12. So that runs on sets with 1 million particles and above. How many particles are in the homework sets? Anybody remember? 2 million? So should be fine. I'm sure that'll fit on the card. And it depends on which cards you have, of course. Some of you might have older GPUs with smaller memory, and it may not work as well. You'll have to try out and see how large of a program you can run. Data set. He did his on an NVIDIA 260. So the prerequisites, you have almost all of them already in place. You already have the Gadget 2 libraries, MPI, GSL, and FFTW. Most of you that are here are either here because of the air conditioning or because you're interested in CUDA. So you've already got the software development kit. You've already got a C compiler. He includes the initial condition generator and the link and the files for initial conditions that go with it. And it's all open source. You can do anything you want with it. If you distribute it, you have to keep his copyright on it. So this is really a wonderful thing. It dovetails very nicely with the workshop. I've sent him an email and asked him if he has any messages for us, and I haven't heard from him yet. So if I get an email back, or if you correspond with him in any way, let us all know and share what's going on. For example, it may be the case that he already knows of bugs. It's a new port. He may know of limitations. He may know what the neatest thing to do next with this set of sources is to get further improvements. Because if you're at factor of 30 on the dominant part of the code and a factor of 10 overall, it means there's still some appreciable speed up that can be found. And he, if one of you wants to do that as a project, you might find that he's a good collaborator. Okay? So let's look at the code a little bit. I have it downloaded here already. Just have to find it. Hang on. Okay, so for some reason, here we go. Okay. So what I did is I downloaded all the source, and I poked around to find some interesting parts to talk to you about. And the piece I'm looking at is the Gadget CUDA kernel GX.h. And there's all sorts of interesting things in here. Let's see. Let me just give you now he's got debugging and emulation. I read the documentation that comes with this. You'll see it's a readme.txt. He has the ability to run it in emulation mode on the graphics processor, either way. And the emulation mode, you can turn on the debugging, and that's very, very helpful because you can get all sorts of information about what's going on. Particularly if you start modifying the code, I would run it that way. On the other hand, you can run it on the GPU, change the code, and see how hard it is to debug. It's an enlightening exercise. So there's a lot of if-defs in here about if the debugging is on, then here is the kind of real CUDA code that does something, and let's look at it. Device here means that this is a procedure which will be callable from the GPU and is meant to run on the GPU. So this is something that wholly lives on the device. So it's some sort of utility procedure that he's going to call from inside another kernel. Has some arguments. Remember, they all have they're all void. And so this is resetting some output when you're in debug mode, and he does some things which we don't need to worry about right now. There's some other ones down here that are a little more interesting. So here is one. I have not decoded all of this, but if you scroll down approximately 200 lines, you'll find this procedure, which is getParticle. Okay, again, it's a device procedure, which means it's going to run wholly on the GPU, called from another procedure running on the GPU. And although I was wrong in detail in something I said in the first lecture, not this, maybe also the second, but in particular in the first, textures can be very, very helpful when you're reading off data from a grid and you need to interpolate. Okay? Because all of that happens in one step for you. It's a built-in procedure in CUDA. So here he has the option to use textures, and then if he is using textures, then he's pulling out information from an array here. It looks like, I'm guessing, a 1D array, and he's pulling out information. So this is using read-only memory that is very advantageous. So there's probably more better examples. I was poking around in here. So if you go on down, this is the most fun part. This is the major part of the code. At line 354 is the force tree evaluate short range. So this is when you're inside the grid, you have a clump of particles. And it's been moved to CUDA. So this is the kernel that does the central calculation of the code that was sped up. So you can compare this procedure and the procedures it calls to the original C code, and you can see how is the parallelization expressed, how is the memory managed, and where the speed up's likely to come from. So this is a great example learning tool. And he even goes over the algorithm for you. So he starts by initializing the variables, looping over particles, and you can all read. He goes through everything. Let's come down a little bit. One thing I want you to see is that this is a fairly long piece of code with lots of actually, some of these ifs are just if-defs, which are special cases. Let's get down a little bit. Here. Well, it's just timing something there. Okay, this is probably calling something, and I'm not going to try to figure it out in front of you. But here we're at step 3J, and it keeps track for you of where he is in memory space and looks at the code. Now, if you compile this with your compiler and save the source, so run it through a pre-compiler, save the source, and look at that, you'll get rid of most of the if-defs, and you'll be able to see a simpler set of code without so many options in it. It's easier to study that way. Okay, but this is about the luckiest thing I can imagine, because it's a code that you're actually using for your other homework that's already written in CUDA. Okay. Now, the next thing, I want to go back to the buffer, to the what's-a-madoodle, the wiki. And I want to go over these exercises. We're finally down to about the size that I expected. And I want to point out to you that there's 3 exercises here. The first, I hope you've done by now, install CUDA on a computer of your choice, compile and run any program in the SDK. Has anybody done that yet? Anybody? Good, great. My favorite in the SDK, the Software Developer Kit, is Fluids GL. If you haven't tried that one, it's really fun. It's a fluid turbulence, and you stir it with your mouse, and in real time it all gets swirly. It's great. Of course, I like turbulence. So there's another one in there with stars. I'm sure you guys like that. Maybe more. Okay, so once you've been able to compile and run an existing program, I want you to write some non-trivial code in C. It could be hello world, but that's a little too easy. I'll give you an example down here. You may want to do something that sums the numbers in an array, something that has a little bit of math, but not too much. Get that running in C, get the answers, and then get that same very simple code to run on the GPU. It's perfectly fine if you want to write a serial code and run it serially and not deal with the parallelism of the chip. I think it's critical, if you're actually interested in this technology, that you try to get some simple code running. And I'm available, although I'll be out of town tomorrow, I'll be back for the weekend and everything else, and I'm available for questions anytime you want to try out code that you've written, okay? So the first exercise is just getting up and running. The second exercise is to get this GPU version of Gadget 2 that we just discussed and compile it. Now, Anjo and I have been trying that for about 4 hours. We have not yet succeeded. So that's a non-trivial exercise. But you have all the sources. So the computer we were using had a slightly non-standard Mac install, and I think he probably built everything for a Unix system. So the makefile makes some assumptions about where things are. And if you've already been installing stuff in preparation for the meeting, and I know a lot of people have because I read all those Google group messages, the same things are going to happen here. So getting it compiled successfully is a major challenge for some of you, and it'll be trivial for others. It just depends on how lucky you are and how close in setup space you were to the author. And then what I want you to do is to take one of Volker's homework problems and do it on your GPU. That involves getting the initial conditions set up. You should be able to use, if you want, data from your runs on your CPU. So you don't necessarily have to get... I think this should be easy. And I think it'll be very satisfying, because you should see, A, that if you've been trying to do the calculations on the computers that we have here at the Institute available to us, you know, there was some scheduling issues and everybody was ending up on the same node. You can get away from all that, you'll have your own computer, and it'll be faster. So you can then pursue more of the homework problems. And then, as I indicated a minute ago, I think it'd be very helpful to take this exam, even if you're not interested in smooth particle hydrodynamics, you're here, you have the lectures, and you have the author of Gadget to ask questions to, and I'll be here most of the time, and there's other experts here, more expert than me on GPU programming. So I think that it's a great time to poke around and take advantage of the fact that you have authors of the major parts of the code and see if you can understand how CUDA works and what the decisions were. And by the way, Volker's not here, right? He is downloading this and trying to see if he can get it running too. He's very excited. They've had a group at his home institution porting it, and they didn't know that this was happening. So he's interested for many reasons to find out how well they did. Okay, the third exercise, and we don't meet again to talk about parallel computing until I think Monday or Tuesday, I don't remember. So there's a few days here to get all these done. The third exercise is to download Flagon, which I'm going to talk about the rest of this session, from SourceForge. I think there's plenty of links that I've already put up that tell you where those things are. Flagon is for those of you who are interested in Fortran. And from the first day, there were a significant number of you that had Fortran legacy codes that you'd like to get running on your GPU. And this is the tool, this is a tool that will let you do that quickly and easily, okay? So if you download Flagon, of course, there's actually documentation. And what I want you to do is see if you can write a simple program, maybe the same one you did up here when you were first trying CUDA. Now write it in Fortran, compile it, and run it, any version of Fortran that you want. And I suggest here that you may want to just create a large array and sum all the numbers in it, random numbers, 1, 2, 3, 4, 5, whatever, it doesn't matter. Do that on the CPU and on the GPU just to see that the code is working properly, and write the result to standard out. This involves quite a bit of, in fact, all of the hard parts that you will quickly become familiar with and forget, but that will stop you from doing anything more interesting if you don't do this, are encapsulated in these three exercises. Compilation, when you have a new product, is typically very hard. There's always cross-linking issues between, in this case, NVCC and whatever C compiler you're using. And now when you're doing the Flagon exercises, there's also a Fortran compiler in the mix. And the Flagon release, as far as I know, last time I looked through it carefully, also requires a C++ compiler. So you've got 4 compilers, cross-linking. There's all sorts of things that can go wrong, but if you're going to be a computational physicist or astrophysicist, those are the kind of things that you need to be able to get through, and it gets easier every time, I promise. So if you get through compiling and being able to write and run a simple C and a simple Fortran code of your choice on the graphics processor, you'll be in good shape. Then you should take the Gadget 2 code and start going through that one loop, follow the procedures that go out of there, and see how you can get the parallelism done in that case, okay? So these examples that's what they are. Okay, so now let me tell you a little bit about Flagon. Yeah.
So just from briefly looking at the source code, it looks to me that this is only the n-body component of Gadget. Is that correct?
The part that I pulled up that I was telling you is the evaluate the tree inside the grids. That's right. And I haven't looked much more deeply because in his little blurb there on his website, he says that's the part that he sped up by a factor of 30. So I think he's done that well. I'm imagining that the other parts, part where you have a grid and you're using that information, are actually much easier to do. But they probably weren't the major part of the time of the code, so he just started with the tree evaluation. As I say, his code was only put on the web 7 days ago. It was great. Terrific luck for us. Okay. Now, let's see. Let me show you a little bit. Okay, I'll do it this way. Bear with me just a moment. Okay. So there's a little code here. I can't talk at the same time as typing. Hang on. That a graduate student of mine wrote to learn CUDA and to demonstrate prowess. Kate produce this code. It's the same kind of code that I was talking about, being able to, it's a turbulence calculation. If those of you that have done magnetohydrodynamic test problems, this is a reduced MHD. In other words, there's just phi and A, electrostatic potential, one component of the vector potential, and it's called the Orszag-Tang problem. So it's a 2D problem with some vortices that whirl around a bit. It's been documented in the literature a long time. It's a good problem for incompressible MHD. Okay, so I just want to show you what Fortran code looks like when it's been put through the crank, and this will run on the GPU. Okay, so is that big enough, or should I try to make it bigger? Can you guys that care see? It's okay? All right. So yeah, program main. There's some modules. Parameters is just a standard kind of module for the code. Here, everything, her standard nomenclature is everything that has to do with the GPU part is prefaced with DEV, or just a D sometimes. So this is device. So there's a device object module and a device Orszag-Tang functions. What are these two things? At a high level, if you were to write something with Flagon, you would just use dev object, and you would not really need, of course you would look because you're curious. You don't really need to know what's inside there. That's a bunch of machinery that helps the Fortran talk to the GPU through C and C++ and CUDA. Dev-OT function is something that you have to write for your specific problem. This is the inner loops of your physics calculation that need to run on the GPU to make the whole thing run fast, okay? And they have to actually be written in CUDA. So we'll get to what that device is. So this one is problem specific, and here OT means Orszag-Tang. That's the problem that she was doing. And dev object is just a module for the overall library. Then this code also has MPI, and as you go through this, you'll see, I don't know if the version, I'll put all this on the wiki for you. The version I'm showing you right now, she was midway between doing the following problem. It's now possible to have it has been for a while, but things are working very well now with the GPUs. You can have a single CPU which talks to, say, 4 Teslas that are all on one board, 4 GPUs. So you have an enormous amount of computing power. You have a conductor and a little orchestra, and each of the cards has 250 or whatever processors on it. So you're writing a parallel program for 1,000 processors, but you write it really for one CPU who farms out all the work. Now the way that we're doing that, in C you have threads, so there's no problem. You just have thread IDs that take care of which process is in control of which of the GPUs. Okay? In Fortran, it's a little bit trickier, and what we're doing, and if any of you come up with a better idea, that's fine, is using MPI to make 4 pseudo processes on one processor. So we have we run as if we had 4 processors, 4 CPUs, okay? And they're numbered 0, 1, 2, 3. Each one of those processes controls a GPU, and then we run it that way. There's undoubtedly other ways, but from Fortran, this was the cleanest way we could get to have a thread and a handle that was good for the whole calculation. Okay, so MPI is here. All right, so initializing looks like this, very common looking code. So at the high level, you're just calling other routines, initialize the GPU, open the GPU module components and get them all loaded up. This is an interesting line, fc_load dev function. It's very interesting. I told you in the second lecture that partway through a calculation, we loaded the program and it ran out of memory. I don't know if you remember that comment. What you do in these calculations is you can, as you're running, you pull in dynamically, you can dynamically link to source or precompiled binaries. And so you're bringing in the code that will help you do one part of the loop, and then you can put that down and bring in another one to do another part of the calculation, all the time leaving the data in place on the GPU. Okay, so you can shuffle the instruction set, which has a limited space in memory. You can shuffle that around, which is very convenient. I haven't used that feature very much, but nevertheless, we still have things up so that we can do that. So you load up a given function, and I'll come back to where this function comes from in a minute. Then you initialize some things. This is all boring. Here's the main step of the code. Call the time stepping. So let's go to that. Okay, so this is what Fortran code looks like when you're writing for the GPU. Again, we defined some modules that we're going to use. Here's the first clue that something is clearly different. We have derived types. The way we've chosen to do it is we define a new type called a device variable. And in Fortran, on the host computer, in memory, the device variable is nothing but a pointer, a set of pointers. Actually, it's a pointers to things on the GPU, and then it's got meta information like the size of the dimensions, the size of the declared dimensions, the used dimensions, the type of the variable, and so forth, right? So it's metadata. It's very small. And so in this problem, she has a parallel, 3 pieces, and then you can do this in what are called Alsacer variables, and in her notation, those were zeta variables. So there's zetas, and then there's the algorithm. It turns out you're going to use an AB3 algorithm, so you need copies for past time steps. Okay, so given these 12 variables, you allocate the device variables. You call them complex. They're in x by in y, and then fill them all with zeros. Already there's a performance point to make here. You don't create the variable on the CPU, fill it with zeros, and then move a bunch of zeros to the GPU, because that takes a long time. And you might as well just create the arrays, do everything you can on the GPU, and never move things back and forth. And so that's what she's done. She allocates everything on the device, fills the initial arrays with zeros on the device, okay? Goes on and sets up her initial conditions. Now these are arrays. It's not device allocate. So these are arrays on Fortran. So these are complex numbers giving some initial amplitudes to some Fourier series. It doesn't matter. And then she calls transfer these complex single precision variables over CPU to GPU is what CTG means. So let's ignore treat as for a moment. So basically, you take the information in a pair OT, which is a Fortran variable defined on the host, and you're putting it on the GPU. When it's not zeros, this is the easy way to do it. So there's a little bit of information transfer, and then we start the time loop. Okay, to go through the time loop, she's going to use AB3, which requires 2 Euler steps to get you going, and then you can carry on with the Adams Bash for 3rd order. So first she calculates on the device the right-hand side, and we'll look inside in a minute, does an Euler step, does another. She's doing the problem 2 ways, it looks like, with A and zeta at any rate. And then is going to do some output. This is presumably to see that things are working properly. Do the same thing again, and then do the real time loop where we're going to use AB3 and a backwards differentiation formula, 2nd order, to do the time steps. So don't worry about the nasty little coding. The basic idea here is, depending on where you are in the algorithm, you do things in a different order. But you're just calling the same routines, AB3, BDF2 underscore step, with different order of arguments so that you can step the equations through in time, okay? And all of this, you see, these are all in Fortran, and it's all happening on the host, and you'll see that things don't really happen on the GPU until we go down a couple of layers. This is sort of metacoding that keeps track of where everything is. When you're done, the end do is the time loop. When you're done, you deallocate everything and the temporary variables that you needed inside that part, and that's the end of the code. Okay, so I thought I would show you an AB3 BDF step. So you can see what the steps actually look like. So this part is a piece of cake. Looks like I've got it queued up to look at the right-hand side, okay? So the right-hand side of some equation that she's solving. So we're going to calculate the right-hand side. We've got A and zeta current, and we're going to get a new A and zeta. So again, we have declared some device variables, and in this case, it looks like these are temporary variables. So she's got some arrays that she's going to use and deallocate at the end, right? So down here at the bottom. So phi now gets declared, allocated, filled with zeros, used in here, and then thrown away. All sitting on the GPU. It never moves back to the CPU. And the code, she's got some kind of inverse Laplace that needs to be done, a Laplace transform. These are basic, since it's a spectral code, these are multiply and divide by k. In Fortran, these would look like very, very simple loops where you would say, for lack of something else, z equals a over k squared, just inside a double loop. Now they're calls, so it's not quite as beautiful. Then there's a call on the device, do the Poisson bracket. So this is a Poisson bracket of phi and a, for example. Then advance a, advance zeta, deallocate, and you're done. Okay, so let's follow the track of dev Laplace. Maybe it's here. Okay. Bear with me just a second. Window's too big. OT functions, right. Okay, I had it. All right. So here's the subroutine dev Laplace. And it's going to put the following simple equation on the GPU. We have some array. We want to do kx squared plus ky squared times the array. So very, very simple. Okay? And this is where I was trying to warn you that CUDA and writing for a GPU can get kind of cumbersome in the notation. But it's not too bad. So she declares temporary variables on the device that she's going to use. This is something we can come back to in about 30 seconds. The way we do it is the way that the threads are grouped together, and the number of threads within a block and the number of blocks used for the whole problems are something you can determine before this at compile or runtime. So you get the block and grid sizes, and you pass all that to one function called devf explicit execute beta. This is all Fortran. You're looking at only Fortran here. And this is the magic of Flagon. There's this one function, which is a device function that I don't know how this name got here. We went through several things. It's a meta function. Okay, so it's going to pick out from another file that we're going to see the kernel that's called Laplace, pass these arguments to it, and execute the Laplace transform. Now, this looks ugly, but it's completely monkey typing to get this stuff right. You have the number of variables, the number of integers in that list, the number of reals in that list. Then you actually have the variables, the integers, and the reals, and so forth. Okay? And then the block sizes and grid thread numbers and all that. So you don't have to think to produce this bit of code. You just have to make sure that it's done correctly. And the key is that somewhere there's a code that says Laplace. So now we're going to find that, and you'll finally see where things got passed to CUDA. Okay, otkernels.cu.
So far I'm thinking about the specific dimension for the arrays, two-dimensional array.
Say it again.
You have in mind a specific dimension for the array at this point, or is something?
Yeah, the dimensions, well, okay, so the treat as was going on behind your back. The way that we found that it was extremely useful to always do things in groups of 16, because the code, CUDA works with batches of 16 called half warps of threads. So it's going to launch whatever you want to do. It likes to launch 16 things at a time and get those done, okay? So we don't want to constrain ourselves to doing problems that are any multiple of 16 in some direction, or any data set that's multiple of 16. So built into Flagon is the ability to, if I want to do something that is 35 by 35, this is a poor example, but I'm going to tell you anyway. 35 by 35, I can define an array that's bigger than that, that's an appropriate multiple of 16, and then use just the parts I want. Moreover, since it's a spectral code, you only need to know, after you de-alias, there's lots of zeros in funny places in that array. And it takes care of all that for you, so that it knows in this large array, there's only some pieces with the key information. And all of that is coded in such a way that it looks like regular placement of Fortran. And you never have to know that CUDA was using larger arrays. You write your Fortran as if it was the size you want, and you just add treat as, and it takes care of it. So here, all you need to know is the number of blocks and threads per block, and it's going to do all of that data. Some of those will be zeros in the general case, but it doesn't cost you very much at all, because there's lots of blocks running, and if one of them, you know, in a corner that I just described where there's actually no data, it doesn't cost you much for that to run, because everything's nice and parallel. So this is the CUDA, and we need to find Laplace in here. Here it is. Oh, there. So this one is not a device call. This is a global call, right? You have the, here, let me go up just a bit so you're not, rats, went the wrong way. Okay, at the top. So the function specifier, it's a global. That means it's called, in this case, it can be called from the host. Could also be called from the device. Can be called from the host. It executes this Laplace function. She's got it commented. It's k squared, kx squared plus ky squared is a. Kx squared is a 1D array. Ky squared is a 1D array. And a is a 2D array. Now, we'll come back to what the get the linear thread ID is. All this is it turns out, is that same block of code I showed you yesterday, block index times thread index plus block index y, that kind of stuff. Just got tired of typing it, so there's a function that returns it. And so you declare the thread ID, the x and y indices, the x and y values. You've got the array A, which at this point is simply a 1D array, right? Because of the treat as trick that was going on, we don't actually deal with, we don't have to worry about things. We can just say A is one-dimensional, and we know where the data is in that memory. And then here, finally, where is it? Yes, here's the actual statement. So scale is equal to, looks like the square, okay, so this is awkward. There's a fast function which can do things like squares and square roots and things like that. It's slightly less accurate. It makes this coding a little bit opaque. This just says multiply these two things together. So you get the kx square and the ky square. That's now scale, which is a float. And then we multiply scale times the array, A1, put that into the result, lap A, wherever that is, and we're done. Okay, so this is the single line of code that does the kx squared plus ky squared, or the two lines of code that does the kx squared plus ky squared times A gives you B. So this doesn't, the trouble is all these other things that go around it. That's where you can be disheartened. But the beautiful thing is, once you've got your data sets figured out, how you're going to lay them out, what the indices are going to be, all you have to do is replace these two lines of executable code, and they're run in parallel, right? Because the thread IDs, what happens is, when this kernel is invoked, it's given a number of blocks, and all those blocks go off and they run independently, each with their sets of threads, and all those threads run independently. So when a microprocessor gets a set of 16 or 32 threads that it's supposed to run. It looks up the thread ID for one, does these 2 execute lines, exits. And that processor typically will run through all those threads and then move on, okay? So this is the actual only little bit of CUDA that we had to write. And then inverse Laplace, you can imagine, is, so there's some stuff hidden here, though. Let me just show you. This complex scale is actually a function that we produced. I'm looking for the definition of it. Okay, hang on. Here's the more complicated loop, just so you can see what it looks like. Here you're doing a whole Adams-Bashforth third order backward differentiation second order step. This is the algebra. It's got several arguments. You do 2/3 and twice that one and half of that one and so forth, right? Where these are arrays and S is the time step. And so it's just a bunch of composed, multiply by a complex number, add, multiply, and so forth. And the thing is, this is all deferred, actually, until you finally get down to what is complex scale. And of course, that's going to be a trivial thing that says z equals a times z. It's just to multiply a complex number by a scalar, okay? Which we wrote so that, well, I don't want to go too deep into the weeds. Okay. Last example here is a reduction. Remember I told you that everything is, my dissatisfaction with CUDA is unfair to the people who wrote it. It is that if you say, I would like to add all the elements up in an array, right? I'm going to do an integral. And I'm in K-space, so all I need to do is add up all the coefficients. Well, there's no such primitive in CUDA that simply lets you add up all the elements of an array. And that's frustrating to me because in MPI, such a reduction is provided for you. So you have to write your own. And Kate wrote this one, working from notes from NVIDIA. And when this is posted, you can kind of work through it and see what it looks like. But let me clue you in. Okay, so this is a sum reduction. It's going to take some array G of floats and add up all the variables, all the values in the array and spit it back out, whatever the sizes are and whatever the numbers are. Okay, now the problem is, of course, that this is data that you want to do in parallel. You want to do this in parallel. And so how do you do that? Well, it's clearest if you start at the bottom, actually. So you're going to reduce lots of elements with each thread, and that depends on how many thread blocks and so forth are available. But looking at this, you can sort of see what happens. You're going to do you have something here inside sync threads, which means this stuff will all get, if there's a group of 16 threads which are adding up some numbers, when they're done, they will reliably wait until they all have their data before they go to the next step. So this avoids race conditions and parallel errors. So you can synchronize that little batch, and then that little batch will, depending on the size of the problem, you're scoping down. So all of this part of the array gets summed down, and that part of the array gets summed down, and that part, and then you take the next level and you sum those down, and you keep going until you get down to just one number. And so at the end of each of these, you've got to synchronize up. And it turns out if you're running in emulation mode, there's smaller block dimension sizes around, so a little bit of extra code there. But this is the kind of thing that I personally found very frustrating because working with MPI for many years, any kind of global, if you want to find the maximum value in an array, reduce max or whatever you call it in your version of MPI, you have to write your own in CUDA. But if we were to work together and share these things as a scientific community, I think very quickly we'll build up a library, because there's certain things that you need to do many, many times, and they're done completely generically. And if they're done right and we can share them, I think we'll push the company to make them part of the release. And they're very open to that. When you give them good, solid code, it immediately becomes part of the release, or they do something even better. So I've been happy in that sense, but frustrated in the sense that you actually have to do it in the first place. Okay. Now I want to show you that meta execute beta thing. Actually, I'm not going to show you. I just want to tell you because it's horrifying. What this does, you have to go through. The beauty of this is that that little Laplace routine was very, very easy to produce. It was like writing a loop of Fortran. You know, once you see that there's some sizes that indicate, you know, do I 1 to 10 or whatever, you see where those pieces go on the page, and then you just write the actual operation down. It's very quick. But to do that for each loop and have kernel calls with block initiators and all this kind of stuff at every time is really painful. So what this does is there's only one custom function that we have to call from CUDA, and it will go and patch in the kernels that it needs. In order to do that, we had to go through C++ and then to do some indirect function pointers, and then C++ had to call C because that's what linked to CUDA, and then you compile with CUDA. So pretty ugly, but it's reliable and it works, and I'll have this up and you can try downloading and writing a simple code with it. Hopefully all this is under the hood and you don't have to see it. Okay, that's what I wanted to show you. Anybody have any questions, problems? Want to talk about another kind of processor than NVIDIA?
So what was the speed up that you got for the particular example?
She got a 32 times speed up on, I think it was 1,000 by 1,000 2D turbulence problem. So that's pretty much what you can get on these machines. So you run into problems with the amount of data that's on the, that you can hold on the chip. So the memory on the GPU it's about, call it 1 or 2 gigs, depends on what's happening, right? So it's a little smaller than what you're used to with a 4 gigabyte per, that you kind of, at least I've gotten used to with my CPU. So it's 2 gigabytes. That's got to hold the instructions and the data and so forth. And then, right, and so they have some tools that help you figure out how much memory you're using in each of the categories, because you have to keep track. Have I used up my instruction space? Have I used up, there's things called registers, which I don't think it's appropriate for the, I have a hard time explaining it, so maybe one-on-one we can do that. The shared memory, if you try to do this reduction and you make the number of threads writing to one of the numbers in this funneling down, then, I mean, you'd like to have everybody synchronized and they all just add and come down, but you have to, there's a maximum number of threads that can share memory at a single time and get synchronized, so you do things in stages. So they have wonderful tools that let you see how you're using memory at each step of the way, and you can see. But fundamentally, when you try to do a 3D problem, you run out of memory. Try doing a 3D problem with only a 2 gig RAM on your single CPU. You can't do a very large problem. And that's an issue. It's now possible to run multiple GPUs from a single CPU, but the communication, so if you can adequately divide your problem with a domain decomposition or a particle, if you're doing a particle code, it's kind of natural to put a batch of particles here and a batch of particles on this processor. Maybe they share all the same space, or maybe not. It depends on the problem you're doing. But you have independent chunks of data on different GPUs, and they're all working very hard. To communicate, again, we have to go through the CPUs, pass the information from, either if it's one CPU controlling 4 GPUs, that's fine. It's not too bad, except that if we all need to communicate at once, you, I, and 2 other people need to all share data, it's all got to go through one CPU, so there's a bottleneck, right? And that begins to hurt very badly if you're not doing a straight Monte Carlo or something that's embarrassingly parallel. So So you get into those issues. And that's where the thing falls down right now for scientific computing. Now, let me show you a website. We have a minute. NCSA. No, not the North Carolina School for the Arts. National Center for Supercomputer Applications. This is at the University of Illinois. Some of you are from out of the country. One way or another, you can get what I want to show you. It's very strange. Okay. They have a Tesla cluster called Lincoln, which has, let's see what it has right now. Where's the pointer? Can anybody decipher this? 1,500 CPUs. I don't know how they count those. Anyway, it's a 47 teraflop machine. It's all Teslas. It's all NVIDIA GPUs with the appropriate number of CPUs to control them. Time on this is free. You send in an application. You say, I'd like to do a test run on multiple GPUs. I have a code ready to go. I've never seen anyone be turned down. You get the time. You can run and see what it's like for yourself on a multiple GPU kind of application. They say that the accelerators, well, let's go down a little bit. Now, so you get a small amount of time for free, and then if you can show that you're using this thing to do an interesting calculation that's vaguely scientific, I've also seen no one get turned down for a serious request for time because the machine is largely underutilized, which means they need people to come in and show how valuable it is and to run on it. So if you get to a point where you can do the fun SDK examples on your laptop and swirl the fluids and do small galaxy mergers, and you want to try compiling something and running something for multiple GPUs, this is the place to run it. You don't have to buy any to try it out. And then they're cheap. If you have success, you can get basically multi-teraflop machine to go on your desk for not too much money. But first you should make sure that it works for you because there's a lot of issues here. Okay. Any other issues, questions? Anybody have any success yet with Gadget on NVIDIA? The makefile was really different than the setup that we had, right? So I tell you, whoever sends me an email first that says they got it to compile, I'll give you $1. Okay. Okay. $2. I'll double it. Yeah. Say it again. Uh-huh. Oh, so for Gadget or for the SDK? Okay, so how far back did you go? 3, 4? So has anybody had success with getting the SDK to compile with a GCC compiler newer than 3.4? Anjor, where are you? You have 4.2, don't you? 4.0 is all, my experience with GNU stuff is if it's 0.0, don't use it. 0.1 and 0.2 are better at any level. 4.4. What have you got? 4.3. Has anybody gotten the SDK to compile on GNU 4.4, the GCC 4.4? If you're having trouble with that, either 3.4 or 4.3 are working for people in the back. Several of you said you got it to compile. What did you use? Do you know which GCC compiler you have? 4.0, 3.7. What else? 4.2. Aha, 4.11. He's ahead of you all now. Any other issues you guys want to share? Has everybody seen the Fluids GL? Yeah, most of you have, I see. If anybody wants to show it to everybody else, we have time. Actually, there's a isn't there a swirly particle one? What does it look like? Yeah. So I've forgotten some of this stuff. They have, so let's say that you want to, you guys can leave at any minute. I'm going to talk for 2 more minutes. One of the things you need to do is find the distance between any 2 points frequently in these algorithms, particularly in-body, right? And that is an intrinsic on the GPU. So instead of taking 32 or 64 clock cycles, you can do it in 1 to 3, something like that. It's extraordinarily useful, and it will greatly accelerate tree type and in-body type calculations. You pay a price, though, in that it's not IEEE compliant in terms of precision. So you're already giving up and going to single precision. Now you lose a couple more digits. So if that's critical to you, be aware. The other thing is all the trig functions are available in a very fast form, which is quite significantly faster, factors of 20 or 30. But again, you lose a little bit in precision. The other thing that you need to watch for is if you're actually using the graphics card, which most of us here in this room are doing, you can be fooled. It will produce a number for you, produce a calculation, and there's no floating point segmentation faults. So if something went bad along the way and the memory flipped a bit and your calculation means nothing, it'll still report it to you just like everything's fine. So it's a graphics card in your computer. If you want them to be IEEE compliant, you pay a little extra and you get the Tesla or whatever they're calling the latest compute GPU. And then they've guaranteed that if it flips a bit or loses some information along the way, that it will stop and say, you got to try again. And they build it to a higher tolerance so that doesn't happen. So, it's fun in games on the laptop, but don't publish anything unless you're quite sure. Anything else? Yeah.
I don't know if you mentioned this, but is there 64-bit support on these cards?
Yeah. It's been spotty, and I'm a little bit out of touch. We had a discussion in the back. Half second. We had a discussion over coffee about that subject, and we differed. Some of us that have been doing this for a couple of years feel like that we bifurcated. It is certainly available now. It's not as fast as single precision. Okay? The question is, will it come up to speed or not? Should we really invest in this stuff? Because for science, we need all the bits, typically. And some people feel that were here in the last lecture that it will probably take years because it's not needed for gaming, and we're a tiny fraction of the company's business. On the other hand, I think that they've just replaced the chief scientists, or rotated out, chief scientists whose main job was graphics for one whose main job is parallel scientific computing. So I think now there's going to be a pull from the top to get these things into place. They're really trying to grab market share. It's a small market compared to video games, but it can be significant. I'll tell you one anecdote. I have a friend who works for a defense company who puts embedded computing into military equipment. And if you want an F-16 to be able to decode what it's looking at faster, then you want the fastest CPU you can get to process the signals that the radar returns. So the government has just bought a bunch of NVIDIA GPUs to put in the nose cones of F-16s. And I said, gee, how's that going to work? So the company makes sure they're IEEE compliant and rugged, and then they have to liquid cool them because, first of all, the GPUs generate a lot of heat, and then you're in a difficult environment. And I asked him, so they add water, and he said, no, we preheat the jet fuel by running it over the GPU. I kid you not. That's cool. Okay, so don't do your laptop on your lap while you're using your GPU. Okay, a couple of key points that I thought of that I just wanted to bring you, make sure you're aware of. CUDA is a programming language. It is not a chip. So it happens to be made by NVIDIA, who makes the G88s or whatever it is you've got in your laptops. But it's a programming language, and the hope is in the community that CUDA will be able to drive all the different kinds of graphics processors for scientifically that come about. So if there's an Intel chip and an AMD ATI chip and the cell and so forth, they're all going to converge in some distant future on one or two operating or programming languages. And NVIDIA is trying very, very hard to make CUDA be the winning programming languages, and so they're going to extraordinary lengths to support other chips. And I think that will come out more and more in the news. So it's not too dangerous to learn CUDA, even if you're worried that NVIDIA is going to get out of the scientific computing business with their chips. The second thing is OpenCL is the superset of all parallel languages for graphics processors, and you'll all get it on your next Snow Leopard operating system with Apple. And OpenCL is a language which can talk to, just like OpenGL was the graphics language, OpenCL is an open computing language for all graphics processors. So you won't have to look under the hood to see which graphics processor you have in your laptop. You'll be able to program with OpenCL and they'll all run. That's great. So why ever look at CUDA? Well, first of all, they're very similar in some ways. Second, I spent about an hour looking at OpenCL code that I found, and it was much, much more voluminous even than the CUDA code I showed you. Lots and lots of lines to specify things. So a smart person could overload that down and get it to a manageable size, you know, with just pulling out the functionality that you need and only linking to that part. But as far as I'm concerned, OpenCL looks kind of scary. So I would advise either, if you don't need to do this now, just wait and see in a year which of the languages is dominant, or go on and work with CUDA because it's the clearest and easiest that I've seen. There's 3 other options, but CUDA's great. Okay, that's it. Pardon me?
What is the 3 options?
Cell BE has its own programming manuals and so forth. That's the IBM. There's something called Brooks. If you were to look up BROOKS, and for a while, I may get the names confused. For a while, Brooks was going to be the programming language, parallel programming language for AMD's ATI, Fire Rage, or whatever it's called, graphics processor for computing. And I've seen people stand up and do demonstrations of how that works. So it's used, but I don't know much more than that. I forget the third one right now. I'll look it up for you. Any else? Okay.